Welcome to my ACL 2022 talk called How Reparametrization Trick Broke Differential Private Text Representation Learning. My name is Ivan Habernal and I'm from Trustworthy Human Language Technologies Group in Germany. So let's get started with some primer on differential privacy. And we'll start with the notion of two neighboring data sets. So we have one data set X, which contains only one person, Elise. And we have another data set X prime, which contains one person, Bob, for example. And we call these two data sets X and X prime as neighboring because they differ just by one person. Now we define something which we call the numeric query. And this is basically a function f, which we apply to a data set and we output some real valued vectors. So for example, a query on Elise X dataset could return a two-item vector of real numbers, and similarly, a query on X prime reveal some information about Bob. And the query is simply something we want to learn about the dataset. So we might have some data that are protected or that are sensitive for Elise, for example, whether she's married or not as a binary value, or whether she's employed or not as 0. And the query might just be an identity function that just copies the input to the output. So basically here we would get the query returning 0 and 0, which corresponds to these two values. So basically we're asking whether she's married or employed, and the same for Bob. So Bob is not married, we get 0, and he is employed and we get 1. Now you're going to be asking how we protect privacy of these person or privacy of these attributes, and this is where differential privacy comes to place. And we're talking about local differential privacy because we're protecting each individual's points. And here, the differential private mechanism, which we entitle M, adds some randomness to the process. Meaning that if we query this dataset X and want to answer whether Elise is married and employed, we randomly maybe flip the second one. So this is not the same thing, this is not 0, this is 1, and through the randomness we're guaranteeing some sort of privacy protection of these individuals. And differential privacy exactly guarantees this. So we only observe this vector Z here, so this is the observation, and it went through a differential private mechanism M. But we don't actually know what these things are, or we can figure it out, but only to some extent. And differential privacy guarantees that whatever we will reveal after observing the output, whatever we reveal about the person X is bounded by some epsilon value, which we call the privacy budget. So the lower the epsilon, the better the privacy, the higher the epsilon, the lower the privacy. There's many ways of guaranteeing differential privacy. So one of them is the Laplace mechanism, which basically adds a random value from Laplace distribution. So here in this example, we do have Elise with one attribute, which is the age, say 25, and we add some randomness and the output will be something different. So the output will be the true value plus some randomness. And the randomness here is drawn from the Laplace distribution, which is zero-centered. And it has some scale which is proportional to the privacy budget, because we want more, the more privacy we require, the brighter the distribution has to be. And here we have something which is called sensitivity, and it's specific to the actual task, so it has to be determined in advance. So far we introduced basics of differential privacy, and now we come to the DPText. So in this paper, actually, in our paper, we examined an existing system called DPText, and which claims to be differential private. So DPText was proposed in a couple of papers by different authors or a group of authors, and they also have a US patent pending as well. And DPText is a simple encoder, takes a document and creates some latent representation of this, and then adds differentially private noise here. So basically takes a vector and adds differentially private noise, and it also learns how much noise it's adding. And what the authors propose is that actually we can learn the privacy budget. So it's a learner parameter. And in order to do so, in order to learn this parameter, the authors employ the reparametrization trick, which is known from variational autoencoders. And here the noise is actually utilizing the Laplace mechanism, which we saw before. And there is one little trick the authors need to use for this reparametrization trick to work, which is sampling for inverse continuous density function. And there's actually two ways of sampling random numbers using CDF, continuous density function, or inverse CDF, basically. And one is this formula, where we first sample standard uniform 0, 1, and then squeeze it through this function, and we get a sample from a Laplace distribution. And there is another version, which we also sample a uniform number, but not from standard for uniform, but from -5 to +5, and then go through this function. Both look similar, but there is some offset here. So if you look at this graph, there is some offset in these, but both will guarantee a Laplace distribution when used properly with sampling from these uniform distributions. And here's the catch, because DPText is utilizing, as we said, the Laplace mechanism and using the inverse CDF or sampling from Laplace distribution to do so, but they take the sampling from uniform and use the other function. So they basically mix up these two approaches for sampling Laplace distribution. And they claim, the authors claim, this is equivalent to sampling from a Laplacian distribution, but it's not. So if you try to re-implement this sampling in this DPText paper, we can compare. So this is a standard Laplace distribution from NumPy. Here, if we sample standard uniform and go through the correct CDF transformation, we get pretty much the same as from standard NumPy, so the correct Laplace. If we use a sampling mechanism, which was used in the DPText, we have two options, because the function is not defined, basically, because of the negative value going to the logarithm. So two options would be we just keep not a number and just sample on and on, or we just transform the nans into zeros. But neither of those will produce like a correct Laplace distribution. And this basically breaks the Laplace mechanism in DPText and breaks the differential privacy. So we have in the paper basically a formal proof by a counterexample showing how exactly it breaks formally and why DPText is not differentially private. But we are also wondering whether we can sanity check DP mechanisms to some extent, and we propose the following things. So we construct an empirical sanity check dataset, and we construct a dataset of two persons. One would be again Elise and one would be Bob, and they have n attributes, which are, in case of Elise, all are 0, and in case of Bob, all are 1s. And if we run this through a local differential private mechanism, it will flip some numbers or change some numbers at some randomness. So here we get 1, here we get 1, and vice versa. And we're trying to be an attacker here, and given this privatized vector, we try to guess what the original values are, whether all 0s or all 1s. And if the differential private mechanism is correct, we cannot exceed the guaranteed privacy loss by definition. So there are some conditional probabilities, and we just basically can estimate these conditional probabilities by using a simulation and computing maximum likelihood estimation. So we run this simulation, I guess, 10 million times to get some estimates of these. And it turns out it's pretty good estimate of the actually privacy loss. So if you implement the correct Laplace mechanism with correct sampling for different number of n, so we try 1 to up to 128 dimensions, so number of attributes, we see that everything which is under the green line is actually correct. So it's not violating differential privacy, and the correct Laplace mechanism is actually doing what it's promising to do. We also looked at EDET, which is another paper which violated differential privacy, which we show in our last EMLP paper. And here we see that as we showed formally before, and now we empirically show that actually EDET is breaking differential privacy to some extent. So here we see everything above the it's crossing the bound on privacy loss, and it's breaking privacy. And in some cases, the privacy loss is infinity, so there's no privacy, but not all the time. However, in DPText, basically, no matter how many attributes are there, the privacy loss is always infinity. So DPText actually does not protect privacy. And maybe that's the reason why why the result on the downstream task looks so good to be true. So that actually draw our attention like, well, something might be fishy in these papers. So this was a short paper and short talk. We proved that DPText violates differential privacy. We have formal proof in the paper, and we have some empirical sanity check algorithm to reveal if a mechanism actually violates DP through some estimations. So if you want to find out more, go to our GitHub and check out the code, and I'll see you at ACL.